Over to you, ma'am. Thank you, sir.
Thank you, Shashikant.
Yeah,
Thanks a
thank
lot.
you, ma'am. Thank you. Thank you, ma'am.
Thank you.
I'm leaving now. Yeah.
Yes, sir. Yes, sir. Thank you, sir.
Thank you. Thank you.
Shaila ma'am,
Yes, ma'am.
Vivek sir has joined.
Yes, ma'am.
Vivek sir,
Let me start the recording, ma'am.
yes, yes. Vivek sir,
Hello, am I audible?
hi. Good evening, sir.
Good evening.
Yes, good evening.
Shall I start with the session?
Sir, wait for 5 minutes. We'll wait
Yeah.
for 2-3 minutes. Yes.
Okay, sure. Thank you.
Sagar, sir, do you have any query? Sagar Yashwantrao?
Screen is visible, ma'am.
Yes, ma'am.
Yes, ma'am.
Poonam, ma'am, you can start now.
Okay. Thank you, ma'am. Screen is visible, ma'am.
Yes, yes.
Yes, ma'am. A very warm and pleasant evening to one and all present here. We welcome you all to our 10th session of 6 days online ATAL FGP, that is Quantum Simulation, Introduction to Quantum Simulation Technologies, and QSimTutorials. I, Ms. Poonam Potraje, on behalf of Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes Mr. Vivek Nainwal sir to the ATAL FGP on next-gen computing, advances in HPC and quantum technologies for the data-driven insights. We are pleased to introduce Mr. Vivek Nainwal sir, Scientist E in the VLSI and Advanced Computing Group at CDAC Hyderabad. With over 18 years of experience in embedded system, quantum computing, and AI/ML. With an executive MTech in data science from IIT Hyderabad, he brings cutting-edge knowledge and the skills in one of the most dynamic fields today. With extensive experience in developing embedded applications, quantum computer simulators, and wireless sensor networks, our speaker is well versed in the intricate world of embedded software ecosystem. Mr. Vivek has also contributed to image processing and deep learning using Python framework. Passionate about education, he plays a key role in workshops and training program advances innovation in IoT, edge computing, and embedded systems. We welcome you, sir. Please accept our virtual token of respect.
Well, thank you very much for a nice and wonderful introduction. So I think I should start off with my session. So I would just share my screen. Just give me 1 second. I think, do you need to disable your screen sharing?
Yes, sir. Done.
Just a second. So is my screen, I think it's visible.
Yes, sir. Yes.
Yeah. So let me start off with this session. So I would like to thank the organizers of this ATAL FDP for giving me an opportunity to present the work that's been done in the area of quantum simulators and what the CDAC has been also doing. So I would give a brief introduction about what is the state of art current technologies that are ongoing in this area, and specifically over the slides I would talk about the indigenous quantum simulator that was developed by ISC and CDAC and IIT Roorkee. So I'll be giving a brief overview of that. So let us start off with the session. I think I have opened a wrong PPT. Okay. Yeah. Uh, so initially, when was the that people started thinking that we should go for a quantum technologies? Like if you talk about quantum mechanics and all, it's been a very long time. It's been over 100 years people talking about quantum mechanics. But it was really in 1980s when the research work was going on for reversible computing and reversible gates that people thought about that why not to come out with something as a quantum computer. And the most notable thing, I think all of you must have known about like Richard Feynman and all. So he had a very famous quote that if you want to simulate any uh, uh, natural thing, okay, that is quantum mechanically, you have to simulate it in a quantum mechanical fashion only. So there was a need of a quantum computers who can simulate your things in a quantum mechanical nature. You cannot do it in a classical fashion. So it has to be in a quantum mechanical manner. So another thing is that when we talk about quantum simulators, so quantum simulation or the simulators are nothing but you can think of as a specialized device that can run your simulate a quantum mechanically things, right? So quantum computers, what we say is they are nothing but a generic computers, okay, that can simulate your quantum mechanical things, right? So ultimately, every quantum computers that we talk about can run your quantum simulations. So there are like for a quantum computer to be well versed, like if you want a quantum computer, there are certain things or certain criteria that has to be met. So these criterias that a quantum computer should meet, this is given by D Venzo criteria. Okay, so if you want to make a quantum computer, the first criteria is that it should be scalable and it should have a well characterized qubits. Okay, second thing is we should be able to initialize your quantum computer to a very simple state. So the simple state in any quantum mechanics is like starting your things with zero. Like in classical computer also, you want to reset a system, you want to start a fresh system, you start with zero. So everything is set to zero and you can start up. So that is the second criteria that was laid forward for a quantum computer to come up. Third thing is you should have a universal gate. Like in classical things, you have the universal gates like NAND and NOR, with the help of which you can make any gate. So there should be a universal gate for quantum. So with the help of those gates, you can perform any operation. Third is because quantum thing is quite unstable. It interacts with the environment. Okay, so there should be a long decoherence time, and these decoherence time should be more than the gate operation. okay, to so that we can run the actual programs on it. Third is there should be a possibility we should be able to measure the things. So okay, so these are the criterias that are governed by a quantum computer. So if you can fulfill these criterias, you can say that okay, we have a possible working quantum computer and we can run a few things on it, right? So there are two ways of making a quantum computer. One is the physical quantum simulators. So physical quantum simulators, I mean quantum computers only, right? So there are various technologies that are currently being used by multiple industry people, academia people, and they've been working on this technology. The most famous is the superconducting qubit technologies, with the help of which you can make quantum computers. The second one is trapped ion, okay, in which the ions are trapped in a magnetic field and you can manipulate them. Okay. The third is photonics qubit. So in the case of a photonics qubit, you have the light photons can be used as your qubits, and the polarization angle can be used as a different states. Similarly, you have quantum dots. So quantum dots are also uh, a nanomaterial that has like very few electrons, and you can control that single electrons for the purpose of changing the information and all. The final is NV Center. So this is just a list of few physical quantum simulator or quantum computing devices that can be used. So there are multiple technologies people are looking and experimenting at. So these are only few of them, not all of them, and there are different ways that you can make quantum computers or simulators. It's not restricted to this one. Okay. Now the second thing is, if you want to make a quantum computer, okay, so the main crux is, or if you want to run a quantum simulation, ultimately what you can do is you can also run the same thing on a classical machine, right? Because any quantum phenomena, what it does is you can mathematically express what happens uh, when a quantum process goes on. So everything is mathematical. So if these mathematical operation can be run on a classical computer, we say that it is behaving as if it was running on an actual quantum computer. Though you will not get the speed up that you get in an actual quantum computer, but the behavior can be very well simulated on a classical computer also. So you can say that a quantum computer simulator that runs on a classical machine. So it has its limitation. So the limitations are you cannot go beyond maybe 20 qubit or 30 qubit kind of a thing, because after 20, 30 qubits, the amount of classical resources that you need is exponential. Okay. So and but the advantage of using the simulator is that with the simulator, what you can do is you can actually validate if you are making an actual quantum computer, you can validate whether the results are correct or not. So if you have made a physical quantum computer and you run a program on that physical quantum computer, you want to see whether I'm getting the correct result or not. So how will you can verify is by running it on a quantum simulator that runs on a classical machine instead, right? So there is a good value add in learning classical uh, quantum simulator also, and as a learning resource they are very good. But for an actual use case, actual real life use case, they might not be as good as a physical quantum computer, right? But they have their own space in learning and all. So now there are different type of formalism according to which your simulators can be designed. A quantum computer simulator. So what you're trying to do is you are trying to simulate a quantum computer on a classical machine. So the most fundamental formalism that anybody uses is a state vector formalism, where qubit is referred as a single vector in the space, right? And the another type of formalism is called as a density matrix formalism. So there are multiple other formalisms also. So, but these are two common formalism that are used. So if you talk about, like many of you must have worked on an IBM simulator and all, right? So it gives you multiple options. It gives you a state vector formalism option also. It has pros and cons. Okay, so those pros and cons maybe I'll discuss in the upcoming slides. So, what's the limitation of a state vector formalism, and what's the advantage of a density matrix formalism? Okay, so these were the most two common ones, but there are other formalism also, like sparse density matrix representation formalism is there, stabilizer representation, graph state representation, max state matrix product state. These are the various type of simulators that one can, if one tries to search in the internet, you will get these kind of simulator options. But most of the people, they restrict to, I think, the state vector formalism only, and advanced users, they go for maybe density matrix representation and all. So they all kind of formalism is there, and there are simulators in open source domain in all these formalisms that are available. Okay, so now coming towards the QSIM. So that was just a brief introduction about what the simulators or the quantum computers are. So ultimately, this session I'll be mostly talking about the QSIM. So QSIM, I'll give you a brief background of QSIM, how it came into picture. So during like 2017-16, IBM had already launched their Qiskit platform, and it had made available the simulators on the cloud. Okay, so Qiskit is a framework that is available by IBM. It's an open source framework, and along with the framework, you have certain simulators, and those simulator was state vector simulators, and you can make your quantum programs and run on it. Okay, so the professor from ISC Bangalore, Professor Apurva Patel, so he is also working in this domain. He figured out that okay, these simulators that were available during that time, the noise and all introduction was not there. So, but in case if you want to run any quantum program in real life scenario, you will find that there are lot many noise that has to be considered. Okay, so then the idea came up that why not to design a indigenous simulator that has all sort of noise and is most realistic in nature. Okay, so when you design any quantum circuit and you run on a state vector kind of a simulator, it runs idly. It does not consider any kind of noises and all. But in real life, you have noise. So that's why the idea came. And along with the IIT Roorkee and CTAC, like the whole this QSIM came into existence. Okay, so what is QSIM actually? So I would say that QSIM is a quantum computer simulator. Okay, and this quantum computer simulator integrated with a GUI-based workbench. So when I say GUI-based workbench means it's a web-based ID. So it has two parts. One is the indigenous simulator built by ISC Bangalore, and on top of it, if you want to connect to the masses, bring it to the people, so a good GUI is needed so that they can use the simulator very easily. So that a workbench is nothing but a web-based ID that integrates with the indigenous quantum simulator. Okay, and what you can do is you can create quantum circuit, quantum programs, and view simulated output. So now the important thing over here is now when this QSIM was being designed, okay, there was a simple notion that we should not rewrite the things that have already been written, right? So QSIM is like an open source software. It is written in Python, okay, and it is added as a new backend to IBM Qiskit platform. So when I say IBM Qiskit platform, IBM Qiskit is a framework. So what does your Qiskit framework provide is it provides like you can write your program, portability, documentation, graphical interface. So all these things we did not want it to touch. Okay, but we wanted to use what is already available in the open source domain and add a indigenous simulator to it. Okay, QSIM. So that's what we did because people right now are very much comfortable with your Qiskit kind of a framework. The framework remains the same. The only thing is you add a different simulator to it. So a indigenous simulator was made and attached to this framework as a new backend. So that if a person writes down his program, he can decide whether I want to use IBM simulator or whether I want to use a indigenous simulator. Okay, so every program remains same. Uh, so the original paper for this simulator is available on this archive link, where they have the authors have mentioned how they have implemented this particular simulator. Okay, the repository is also available at ISC link, so or at a GitHub link of ISC, and with the name of Qiskit Akash. These are some binder links. You can also try it online directly if you want to. So user guide is also available. So now coming towards like the early gate model or full stack players that are currently available, and people use these frameworks if they are working in this current domain. So the most important one is your IBM Quantum. So everybody knows that they have a full stack. They start from the bottom, and simulator they provide the quantum hardware. They have a framework that is available for writing program. They have a libraries available, and few applications also, demonstrable applications, right? So Google also provides similarly a full stack for your quantum programming: Rigetti, Xanadu, Origin Q, Pascal. So this is, I think, for 2022. So in the past 2 years, we have seen tremendous growth in the quantum players, and I think this the full stack players have also increased. So these are the most common one. So because the QSIM is based on Qiskit, so I would like to tell that what's the structure of the framework of the Qiskit. So if you look at this particular, just let me, okay, pointer. So if you look at this particular diagram, it shows you layer-wise approach, like where is the Qiskit and what features it provides. So if you see at the bottom thing, it says Qiskit Air, and you have written something called as a simulator over here, right? So Qiskit Air is a component in your Qiskit framework that provides a simulator. So it has a high-end simulator that can use multiple CPUs or GPUs. Okay. Similarly, it has a hardware provider. So you have uh, code or libraries available with which you can actually run your code on actual IBM machine or AQT machine or INQ machine. So on top of it is there is a Qiskit Terra. So Qiskit Terra is the main thing that provides the core capability. When I say core capability means, if you want to design a quantum circuit, you will use the Qiskit Terra library for designing your code and all, for visualizing your circuit and all. So this is where we thought that why not to put uh, QSIM. So below Qiskit Terra, where simulator is there. So instead of Qiskit Air, we have added one more component, that is your QSIM. So you have a choice whether you want to run it on the Qiskit Air, or whether you want to run it on the QSIM, or whether you want to run on an actual hardware. On top, if you see, these are the high-level application and libraries. So these are independent. So this can be anything. So here in Qiskit Air, one more block has shown up where we have put a QSIM. Okay, so it has a whole uh, library or the Qiskit software stack. If you see, it has multiple libraries: Terra, Air, Nature, Finance, Optimization. So all these get installed. So if anybody is well versed with these things, they can easily run your things on your QSIM. Okay, so any quantum program, if we see that we want to run, so there are basically 4 steps to do the things. The first thing is you build a circuit. Okay, you write down the logic or represent your problem depending upon the gates. Then you compile the circuits. Okay, so compiler is there. You run it and then you analyze it. So these are the 4 basic steps that any quantum programmer will do. Okay, no matter whether it is IBM or whether it is other stack providers, this is what you do. Okay, So this four steps, if you see, when we talk about a Qiskit framework, so this is how it is done. First, if you see on the top uh, right corner, the first step what you do is you import some libraries. Okay, from Qiskit import star. Okay, so this is what you do. Second thing is you create a quantum circuit. So quantum circuit will be based upon your algorithm or whatever things are available. So you create an object of a quantum circuit. So this quantum circuit is provided by your the library or the framework. And then you write down the logic. So if you see over here circ.h0, so that means you're applying a Hadamard gate on the qubit 0. Then if you want to apply a 2 qubit gate, so cx01, you are applying cx02. So you can see on the right side, this is a kind of a quantum circuit that will be generated. So writing program using these are very easy, but designing algorithm is difficult, right? So there's not much hard work in writing or coding these things, but algorithm designing is what is tough. So now if you want to simulate the circuit, you have uh, made the circuit and want to simulate it. For Qiskit, what you do is you import air. So air is nothing but a module that provides a simulator to you. So initially in the slides, I told that there are various types of simulators that are available. So from the air module, you can get a state vector simulator as a backend. And now once you get the backend, you can simply run your circuit using this particular API, backend.run, and you pass a circuit to it. So ultimately, it will go as a job, it will run, and it will get back the result. So the final output is you analyze the thing, what is the output of your thing, you get a state vector. Okay, so this is the four steps that you do in any quantum program, right? Now coming to your QSIM. So what changes in QSIM? Okay, and what is the difference between the QSIM and the normal Qiskit kind of or a state vector simulator that Qiskit does? So here, if you see, like everything remains same. There is very minor difference. First, we are importing the libraries, whatever we are doing, but there is an additional dictionary object that we have added up. So this dictionary object, if you see, it has various kind of noises that you can put into your code or into your circuit while simulating. So you have rotation error. So I'll give a brief description about each and every error. So they are rotation error, okay, TSP model error, thermal factor, decoherence, depolarization, Bell depolarization, decay factor. So when you say 1, 1, 1, 1, if you see over here in this dictionary, everywhere it is written as 1, right? So this is an ideal case. That means there is no error. Okay. If you want to introduce the error, you need to change these values. Okay. So a programmer who knows what type of noise he wants or introduce. So depending upon that, he will change or introduce the error in these values. And if you see in the third part, what we are trying to do, so like here, the first part was like a program on the QSIM. Second was circuit. So if you see, when you are making the circuit on the right hand side, there is no change. So this is the way you write your circuit in a Qiskit, and this is the same way you write your program in QSIM also. So there is no change in the algorithm or the way you write the circuit. The only thing changes is you add an additional dictionary, but instead of getting the air module, what we do is we use the basic air module and get DM simulator. This is our own simulator, the QSIM, density matrix simulator. So I'll talk about density matrix also. This is the DM simulator you will get. And when you want to execute this, you pass the first parameter is your circuit that you pass. Second is the backend. And third is the noise options. So these are the noise option you pass. So this is the only change that you do. And you submit the job and get the results. Rest everything remains same. So only two changes are there. Adding of the noise dictionary, choosing R simulator instead of air simulator, and passing the noise option while executing this thing. So anybody who has written a program in Qiskit, the same program, he can also run on the QSIM with minor changes. very, very minor changes. Okay. So now if you see, I was talking about state vector and density matrix. Okay, so let us come to a thing. So, like the standard formulation of your quantum mechanics, your states are vector in a Hilbert space and they evolve by unitary transformation. So, the unitary transformation they evolve is given by psi goes to u and ket of psi. Okay, and this evolution is deterministic, continuous, and reversible. So this is how your state vector simulator works. You apply a unitary and it goes from one state to another state. Now, this type of formalism is good for describing the pure state of a closed quantum system, but it is not sufficient for describing the mixed state. Right? So, the mixed state comes when you are dealing with the environment and all. Your quantum system is in constant touch with the environment, and you have all sorts of noises that hampers that. So when that kind of scenario comes in, you have a mixed state, and these mixed states cannot be purely simulated by a simple state vector kind of a thing. So if you want to simulate a quantum system in the most generic description, so that you can do in the form of a density matrix. Okay. So this slide usually tells about like the generic things. The quantum systems are sensitive to disturbances from environment, and like even the small things will hamper them and perturb them. So, and the important thing over here is now all the devices or all the quantum computers that you are looking right now, these are noisy in nature. Okay, we've not been able to bring down the noise of these quantum computers to a very low level so that they can be used for an actual application, right? So all these noises still exist, and we need to reduce it as much as possible so that we can make some what do you say, a good quantum computers, right? Okay, and these devices are named as noisy intermediate scale quantum system. So whatever quantum computers are available, there is a term for them: noisy intermediate scale quantum system. Why? Because they still have noisy qubits, and when you run your code or quantum program, they are affected by these noises, and you won't get the idealistic result that you are expecting. Okay, so you need to take care of that. Okay, so if you write a program and run it on an idle simulator, you will get an idle answer. But if you run the same thing on a hardware platform, you won't get the correct answer. Okay, so roughly right now, if you see the quantum computers that are available, they are in the range of 10 to 100 qubits. Well, IBM has gone up to maybe 156. They are right now giving 156 qubit quantum computers for everyone. Okay, and recently I was also looking at one news. Even China has come up with a quantum computing platform with 504 qubits of superconducting thing. And recently, Google has also launched one Willow chip, and I think it was day before yesterday only. It was in the headlines that they have solved the problems in 5 minutes that would have taken uh, like 10 septillion years or something like that. So the number of qubits are increasing, and people are working towards bringing the noise level down. Okay, so these are the kind of errors usually that any quantum system will come across. The first thing is the imprecise initial state preparation. So any quantum system, when you initialize the state, you need to be precise that if I want this state, I should be in that state. Okay, but ideally that will not happen. If you want to start from 0000, it is highly unlikely that you will start from that state, but there might be some disturbances. Imperfect logic gate implementation. So various quantum computers have different types of quantum gates associated with them. and these gates will have uh, different error. If you manufacture one gate, okay, the fidelity of one gate will vary with the other gate. Okay, so the simplest example is maybe X gate is there. Okay, so X gate makes 0 to 1, right? So 0 to 1 is nothing but a rotation of 180 degree. But if there is some error in the gate implementation, you might not get exactly 180-degree rotation. You might get 179 degree or 179.9 degree. Okay, so every time you will not get rotation. Disturbances of data in the memory. So as I said that there are errors like decoherence and decay that will come into picture. So if you have a quantum system in a state 0, it will not always remain in state 0. It will change its state to something else. If it is 1, it will deviate from that because of those things. Error prone measurement. Finally, when you compute or run your program, ultimately you have to make measurements. Now, when you make the measurements, the errors will be there also. In the measurement equipment also, the errors will be there. So now, if you want to design a realistic quantum simulator, you will have to include all these kind of errors with an appropriate probability distribution. So this is what is done in your QSIM. So QSIM has taken all the types of errors, and in a density matrix formalism, it has included all these errors. And when you run your program, you can choose these errors, like what, how much is the value of my error and how it will affect my program. Okay, so these are the some few I think features of the QSIM. So it has an ID that is Python based. So I'll go through that. Maybe I'll directly go to the website and show you that where you can access it and see. Okay, so I think these are the features that your QSIM provides. So let me go to the website directly and show you the features where you can actually access this QSIM and how you can access it. Okay. Okay. So hopefully you are able to see my screen. So there is a site. So QSIM is available on a site qctoolkit.in. Okay, so if you write down qctoolkit.in, you will land up on this particular page. Okay, and if you want to get an access to it, so I think I've already logged in, so I logged out so that you can get. So once you want to log in, what we have provided is uh, earlier people used to write an email to us requesting an access, and we used to create account for them. Okay, so but later on to attract a larger user base, we had integrated Google login. So you can use your Google ID also and directly use it, or else you can write an email to us. So, so there is a email address qcworkbench@cdac.in. So if you write down a simple mail that okay, I want an access to the QSIM, we'll create the account for you and send the details. Because sometimes we face problems with the Google plugging in also. So that's why. So so once you go to the site and you hit a login page, you can go through the Google thing. So let me just log into my account. You can okay, and if we log into this one, it will land up you on this particular page. So this is a web-based ID kind of a thing that will help you write your programs or use QSIM. Like if you want to try out QSIM, this is the first thing very easily what you can do is you can just come to this page. So if you see, it has a default Python editor that is available. And when you land on this page, you will get a template code. So this is a very simple code. So if you see this particular code, you have same, the libraries are imported, then you have the noise option, then you have a quantum circuit. So if you see, this is a very simple quantum circuit that has been written. Okay, it has 3 qubits. Okay, and we are adding a Hadamard gate, and we are measuring it. So that's it. And you don't need to visualize. If you want to visualize it, if you see that it will automatically construct the circuit for you and show the visualization. If you want to change anything, like if you want to add a Hadamard gate to a second qubit, you see dot H and Q of 1. Okay, and what we need to do is, like, this is your program. If you want to reconstruct the shift enter, we need to press. So here, if you can see, it's written over here that press shift enter to generate a quantum circuit. So I have just changed or added a Hadamard, and I want to visualize my new circuit. So you can see that, okay, Hadamard gate is there, and you have the same circuit. So once your circuit is done, you get the DM simulator, okay, and execute with the options. So options are nothing but the noise option, and you can visualize the result or the density matrix. Right. So this is a very simple code, comes with a template. Okay. Now coming towards the other parameters that are available. Okay. I was talking about noise parameter, and I talked that what are these noise parameters. So if you see on the right hand side, we have GUI where you can actually change the noise parameter. So if you see, you can change the noise parameter, and automatically it will change this in the code. So you have a choice. You can directly edit also, or else you can use this particular UI thing. Okay, but um, how do I understand what does this rotation error means? Okay, for a new person he's to talk on this quantum computing, okay, he want to know that, okay, what is this rotation error? So there are some help texts that are available. So if you click on this particular icon, so this is an information on rotation error. So rotation error is nothing but a single qubit error that is available. Okay, and a single qubit rotation is set and have a fixed rotation axis, and we denote them as Rx, Ry, Rz. We assume that the error arises from the inaccuracies in the rotation angle. So I was giving an example previously that if I have an X gate, okay, and when I apply an X gate, okay, in an ideal condition, it will rotate 180-degree, right? But because of the error, it will not rotate 180-degree. It might rotate a 179 or 175. So this is where you can actually put that value. Okay. So this is your the value about the mean. Okay. So the all information is available in this rotation error. Okay. So this is the rotation error. Now, what do you mean by TSP error? TSP is transitive selective pulse. Okay. So this is a 2-qubit error. Okay. So we have a 1-qubit error. We have 2-qubit error that applies on a 2-qubit gate. So ultimately, this TSP error is a 2-qubit error, and it is applied on a C0 gate. Okay, and this is where you can do the things. So one more thing I would like to bring to your notice is, like, when we talk about simulators. So I was talking that this is a QSim and this is a density matrix simulator. So it must have a universal set of gates. So this DM simulator, when I'm talking about universal set of gate, it has 4 gates. So with the 4 gates, this whole simulator is made. U1, U2, U3, and C0. Okay. So with this 4 gates, so no matter whether you put Hadamard or other gates, your Qiskit platform, it has something called as a transpiler. Okay. So you write a algorithm with whatever gate you want. Okay. It goes to your transpiler. The transpiler will see that, okay, my backend is DM simulator. It has these gates, U1, U2, U3, and C0. It will convert your whole code into those gates. Okay, because ultimately it has to run your program on the DM simulator. So that's the job of a transpiler, right? So if you come over here, we have another type of error, decay and decoherence. So if you see decay and decoherence are what type of error? These are memory errors. Okay. So the description of that is also available over here. Open quantum system undergoes decoherence and decay, irrespective of whether it is being manipulated by some instruction or not. Right? Even if you don't apply any gate, still your things will change. Right? And these effects cause maximum damage to a quantum signal because they act on all the qubits all the time. So these memory errors you can introduce by decay and decoherence error. So this is the same thing, decay and decoherence. Now you have depolarization factor. So this is a single qubit measurement error. So this is a measurement error that you can put in your code. Another type is thermal factor. So thermal factor, it talks about the thermal nature of environment. Like uh, like if you want to start your qubit, okay, it might not be in the ground state. So what is the probability that your qubit is not in the ground state? So in your code, you always see that you write down your this program, and you always start with the ket 0 state. But there is a little chance that your qubit might not be in the ket 0 state, right? It might be in a different state. So what is that probability? So that probability you can introduce by the thermal error, the probability of the initial qubit to be in the ground state. So if it is 1, that means it is 100% probability in the ground state. If it is something else, it will change, right? So similarly, you have two qubit measurement error also. It is called as the Bell depolarization factor. And you can simply introduce them by the changing these values. Okay. So these were about the various type of errors that you can introduce in your quantum circuit, right? And there is one more thing I wanted to tell. So there are different type of measurements also that is available. So if you right click on the measure, so if you right click on the measure, it will say single qubit measure, ensemble measure, expectation measure. So your QSIM also provides different kinds of measurements, okay, where you can partially select a few qubits and run your measurement. Uh, it also has a Bell measurement, like it can measure uh, two qubits simultaneously also. Like Bell measurement is also there. So it is not available on the UI, it is not showing over here, but it supports that. Okay, so this was the main UI interface. So there is one tab that talks about the basic codes or the documentation of this thing. So if you want to look that, okay, what packet to import and how to use it, you have small help section available over here in form of documents, how you can create a quantum circuit, how you can use a quantum resistor, okay, how to use in gate, different type of gates, whether it is the Foley gate, control Z gate, S gate or a T gate. So everything documentation regarding this are there. How you can include options and how you can run the execution. Okay, so this small thing is here. Now suppose if you want to run this uh, code, what you need to do is on the top there is something called as the run circuit. So this is just a button that you need to hit, and what will happen is this circuit will run and go on the HPC machine. So on the run circuit side, if you see, there are two things that are selected. Select backend. So these are the supercomputers that are available. Uh, so Param Utkarsh is at CTAC Bangalore. Param Shakti is, I think, at IIT Kharagpur. Okay, so you can choose any one of them, because sometimes what happens is because of the maintenance activity, one or the other is sometimes down. So you can choose whichever one is available. These are huge systems that are parallelly accessed by other people also. So when you run your circuit, you will see. So let us run this circuit. So when I hit enter, it says okay, submitted the simulation ID. It will give a job ID, right? So it does not run interactively. Okay, this job ID is created. This circuit will go to the your scheduler of your supercomputer. Okay, and it will be run. So here, if you can see that it is in a queued state. Okay, because many people are running the things, resources are not always available, but they will be like whenever it is available, it will start running. And once you run your code, you can see, or if you click on this particular thing, if you see, you will you can see the output of your code. So this is a previous code that I had run, right? So it will show the output in this format. It will show error if any that is available, what code you had submitted, it will show, and what circuit you had submitted, it will show. So anything you can do. And what you can do is you can actually re-edit. You can re-edit your code. You can use the edit button and change code and again submit for the execution time. So currently your QSIM, if you see there is a limitation to it, it can currently simulate 12 qubit of code, quantum circuit. Okay, so if you try to execute a code that is beyond 12 qubit, it will take, like, it will throw an error, frankly speaking. Okay, so right now it is 12 qubit, but in the coming uh, time, I think we are working on increasing the number of the qubits. So hopefully 15 to 16 we'll be able to run. So on the right hand side, if you see, you have a tab that is called a simulation. So this simulation tab will show you all the previous code or simulations that you had run. So these are the many things. So the latest one that I had submitted, I think in the Paramutkarsh just now, it has completed, and you can actually view the status of it by just clicking onto it. Uh, Another tab is your example tab. So this consists of various programs that are available, like uh, if you want to see how an entanglement works. So this is an example program for entanglement. How does a Hadamard gate behave? How does a NOT gate behave? Toffoli gate behave? So you can just click on this, and what it will do is it will reload that program and will make available to you. So this is the same program that we had seen. So in the example section, directly you can use. So there are a few examples that we had a course with IIT Roorkee. So they had also provided few programs that are available. Few algorithms are there like Deutsch's algorithm, Burson-Rani, half-adder, Grover's, QFT. How you can view this? You can simply click onto it, load it, and run it and try it for yourself. So all these examples are available. So uh, there is actually different options also. I forgot to tell if by looking at this initialization measurement, actually I remembered that there is uh, many things I forgot. Okay, so let me go back to the main page. So I forgot to show these options, right? So simulation options are there. So one is plot option. So plot option usually will plot the final probabilities and all that you get if you enable this option. Otherwise, you can always use matplotlib. So there is no restriction to it. You can, if you want to plot any of the visualization, you can simply import the matplotlib library and plot them for yourself. Shows partition is this is an option actually for debugging purpose, not really for a programmer, but it only shows your how it has partitioned your circuit. Okay. Now, when you make your quantum, okay, you might use multiple gates and all. Okay, so what your ISC team had done was they had made an internal optimizer. Okay, so if you write your code into some gates, it will go to their optimizer. It will try to reduce the number of gates, because if your program is having more number of gates, your answer will be not correct. So we try to limit the number of gate or the depth of the circuit to the minimum. So they have an optimizer that tries to do that and tries to fit into the various cycles. Okay, so that mm, uh, you have minimum number of gates, and how what gates can run in one clock cycles is given by this partition kind of a thing. So this not that much useful for a programmer. Okay, but for a debugger, they used it for purpose. So run on a GPU. So there is an option for running onto the GPU also. So when you turn on this option, what will happen is previous simulation that I had run, it was going into a CPU. It was running on the CPU. But if you check this particular option, it will enable your code to run on the GPU, the same code. But usually the queue times is more in the GPU because many people use the GPU for training and all. So, so if you have a bigger program, then I would say that you use this option. Otherwise, use the normal option. You will get the result in the fine time, right? So this was GPU or CPU, both you can run, and qubit initialization. So this is one option actually I forgot to tell previously. So as I told you that when you start your quantum program, if you see, we have uh, the initial state as 0, 0, 0. By default, it's cat 0, cat 0, cat 0, right? But QSIM also provides other option that instead of cat 0 state, you can actually choose your state based on a binary string. So if you want the first qubit Q naught as 1, second as 0, third as 1, you can put that thing as a binary string. So when you click this option, so this option will show you, I think, binary string and initialize according to 0, 1. So whichever qubit you want to initialize. So here what we are saying is 0, 1 means the zeroth qubit will be initialized to the zeroth state, 0 state, and the qubit 1 will be initialized to the 1 state. So if we make it opposite, like 1, 0, if we say that qubit 0 will be initialized to 1 and Q naught will be initialized to 1. So don't go on the visualization part, though it is showing 0, 0, but it will get initialized. So that option is there. So similarly, you have maximally mixed state, uniform superposition state, and thermal state. So these are the four initialization option that you can choose while running your circuit. What is the initial state of my circuit? What is the initial state of my system before running your quantum circuit? So you have these multiple options available with you. You can choose it. Okay. So here, if you see, there is one more option about DMSIM. So if you click on this particular part, it will lead you to the original work or the publication where you can see how these simulator is being implemented. Okay, you can go and read this particular paper. Okay, another is open in a notebook. So many of you are much more convenient to work with the Jupyter notebook and all. So there is something called as a my binder. So when you hit this particular link, what happens is it will take you to a site called as a my binder. So my binder is an interesting site. What it does is this is not only true for your quantum simulator, but suppose if you have any code that is on a GitHub and you want to try that code out, what it does is in the my binder, you simply give a link of the repository, GitHub repository or something like that to the my binder. What it will do is it will fetch the code, it will make a container, and it will run that container and give the output of console of your container to you. So if you see, what I did was I clicked on the link and to the my binder. So that link was pointing to the repository of your QSIM, your ISC QSIM. So the container was already there, and you can see that this is a Jupyter notebook that has opened up. And when you click on this particular notebook, you can actually see. So right now, I think it's not opening the notebook, but ultimately you can run all your code in the notebooks also. So these are some few examples that you can look at how to initialize measurement, partition, noise, visualization in a notebook kind of a fashion. If you don't want to install it on your laptop. Okay. So this is one way of running your QSIM through your QCToolkit.in site. Okay, just you want to test it. But you can also install your QSIM or the DM simulator in your local machine also. It's not restricted that you have to use the QCToolkit.in site only. You can actually install it on your laptop also and work it in a Jupyter notebook fashion. So I think in my slides, uh, just I'll open the slides. So I think I have already gone through these particular things, login stream, UI and all. Okay, I think I have forgot installation part. There was one installation. Okay, I think maybe it is. I think I have missed that slide. So maybe I'll update that particular slide. So that slide actually shows how to install your QSIM onto a local machine on a local laptop, right? So maybe just I think I have. Let me see. I'm sorry for changing the slides too much, but okay, I think I missed out this slide, right? So if you look at this particular thing, so you can install QSIM. QSIM, like the web UI won't come, but the simulator you can simply come. So these are the particular steps that you can follow. The simple way, like you install a Miniconda, then you activate the environment, and in the environment, if you see, you create the name of a Conda environment. Okay, and then this is the real part. If you see over here, okay, so we are cloning the repository. Okay, we are checking out a specific version. So there is a specific version. So this is that SHA of that particular version that works fine. You need to check out this particular version and then pip install and then run pip install Jupyter Lab. So this is the only thing that you need to do. The rest, I think most of you, if you have worked on any AI-based project or something, you are well versed with how to work with Jupyter Lab or Jupyter notebooks. So this is the clone the stable version of QSIM. So this is how you can install it on a laptop. And in your laptop, about 10 qubits you can easily simulate. If you go beyond 11, 12, 13, 14, your RAM won't be suffice and it will take larger amount of time. But for testing smaller circuits, you can always use a laptop or QC Toolkit.in site. So I'll show you maybe, I think I have, okay, fine. Okay, and I'll come back to this. So let us, coming back to the main thing. So now, as I told you, that if we have any quantum circuit and want to see that how the quantum circuit behaves with noise and without noise, this is how you can do it. So let me go to an example. Before going to an example, what thing I would show you is a quantum circuit. So take for example, this is a quantum circuit. So this quantum circuit is for 2-bit ripple adder. Okay, I don't want to go into like details like how I have come with this particular thing, but okay, this is a quantum circuit and it is a 2-qubit ripple adder. What does it do is, it is a classical circuit, so it is not entangled or something like that. Okay, so now if you see, what we are trying to do over here is, we are trying to add the input A, that is 2, the input B is 1. So that means 2 plus 1, we want to get the output as 3. Okay, so suppose this is a quantum circuit and it simply adds two things, 2 plus 1, and output we should get as 3. Now, if you want to see that how the error will change the output of this particular circuit. Okay, if we run with noise and without noise, if you want to see. So let us go to the main program over here. Okay, so there is an example available already. So if you go in the algorithm, there is 2-qubit ripple adder. So if you hit this particular thing, okay, 2-qubit ripple adder, what we do is we'll change the, maybe let me shrink this. So this whole program is there, okay, ripple, and we want to see that how does this change. So let me make it change what we'll do is we'll introduce a decay factor of 0.99. Like if we run this circuit with a slight change in the error. So here if you see there are two dictionary. Okay, one is option without noise, one is option. So this is with noise. And what we are doing in this program is we have a circuit that we have built. Okay, and we are running this circuit two times. One, we are running it without noise. Okay, second time we are running it with noise. Okay, and getting the results. And ultimately, what we are doing is we are plotting that how the answer changes with noise and without noise. So this is nothing, just getting the answers and all. Okay, so this is just plotting function and all. So the crux is run it two times with noise and without noise, and just plot that what would be the output. So when we run this particular thing, okay, run circuit. So I think it will get submitted. It might take some time. Let us see. Okay, it is running. So it should show. I think I have already previously also run this thing. So let us go to the result page. I think it's still showing running. It might take maybe 30 seconds or something because it's not that much big circuit and it is already running. So let us wait for some time. Okay, still it is running. Okay, so here is the output. So what we did was we ran the circuit twice and ultimately we plotted the probability. So here if you see without noise, when we added 1 plus 2, there is a 100% probability of getting 3 because this was idle simulation. But when we introduced the noise, so the noise was what? If you look at the code, the noise was we changed the decay factor just by 1%. So we added 1% decay factor because decay, it applies all part of the circuit all the time. Okay, so it has a severe impact. And you can see by the graph that now the probability, though the probability of getting 3 is high still, but it is distributed. So there are other probabilities also that have come into picture. So this is what the noise does to your program. And this is how you can run your program and see that if you run the same thing on a noisy quantum computer, what result you might get and what not. So this is the main crux of this particular simulator, that you can simulate noise, right? So now coming to the other thing, like I was saying that you can also install it on your laptop. So I've already installed it on my laptop. Okay, and if you see that this is the same code, like the 2-bit triple adder. Okay, and the same thing what we are doing over here is we have without noise, with noise, and these are the code, and ultimately we are printing the thing. So you can either use the QCToolkit.in or you can always install it on your laptop. So if you change the noise, like if you make it both 1.0 or maybe instead of 0.999, okay, so 0.01% error if you do, so run, I think, run all cells. So I think if you come, so the probability is high because the error is 0.01. So still the probability is 0.934. Okay, but when you was having like 99%, it was decreasing. So as you keep on increasing the error, you will see how your output varies. So let us put 0.9. Okay, so in 0.9, I think again run all cell. I don't think we will get much answer. See, so if we introduce an error, that is point 0.9. That means 10% error in your decoherence, you won't get the correct answers. So you will get 0, right? But we are expecting 3. So this is what your noise does, and this is how you can do. So you can run it as a notebook also, or you can run it on the this QCToolkit.in also. So this is what is the main crux of this particular slide. Let me, this is, okay. Let me again go back to the slideshow. Okay, so coming back to the slideshow. Now, if you see, there are many countries. So they are looking at various technologies. Okay, United States, if you see, they have all sorts of technology: superconducting, ion trap, photonics, neutral atom, semiconductor based, and the different companies are also listed who are working in this particular domain. So different countries have different focus areas. So these are various companies, and most of them actually, if you today, if you want to try out, they provide access to, like, over the cloud. Most of them provide access, but with a limited time frame. So now there are some good resources for you to learn on the quantum computing. Like if you go 4 years back, you have very little resources, but in the last 4 to 3 years, you will see that internet has exploded with the quantum computing resources. But these are some few links that we have. So along with CDAC, IIT Roorkee and all, we have conducted few online courses. So short-term courses, around 20 hours of material is there in that. You can always go through this repository. So the codes and the playlist is available. In 2023 also, we conducted a course in which you have slides, you have assignments that are available, and the lecture material is there. Recently, like 3 or 4 months back only, ISC Bangalore actually runs your MTech in quantum computing. So they had started in, I think, 2022 or 2021, I think. So the lectures for quantum computing by Professor Apurva Patel, who has written the core simulator of the QSIM along with his students and all. So his lecture, around 30 to 35 hours lectures are there. So what is being taught in the ISC, those lectures are available for you. And I think if you want to go into deep depth of your quantum computing, I would highly recommend this particular thing, Introduction to Quantum Computation by ISC Bangalore. So even if you just search it onto YouTube, you will get it. But this is the link that is available, and it is one of a very good resource that is available. It specifically talks about density matrix simulations. So many people talk about only state vector, but here the focus is more towards how your density matrix simulation works. Okay, so now coming towards a few of the works that we are currently doing in CDAC. So we have something new project that is HPC-based quantum accelerators for enabling quantum computing. So here what we are trying to do is we have various simulators that are available, and these simulators we are trying to put it onto an accelerated platform, maybe a GPU platform or a vector platform, an FPGA platform, so that we can reduce the simulation time and increase acceleration of the classical quantum simulators. So that is one project. Okay, so this is what is we are currently focusing on. We are focusing on QSIM density matrix simulator. So right now, as I said, that this site provides the QCToolkit.in. It has a limitation of 12 qubit. So with the help of these cards, what we are trying to do is we are trying to put it on the GPU card, and right now we've been able to achieve up to 16 qubit. So with a GPU card A100 with an 80 GB of memory, we are able to run 16 qubit density matrix simulator. Now the challenge between density matrix and the state vector simulator is that Your density matrix simulator, the number of coefficients in your density matrix is 4 raised to power n. Okay, so 2 raised to power 2n, you can think like that. Okay, in the state vector, it is only 2 raised to power n. So a 16 qubit density matrix simulator uses a huge number, like 2 raised to power, no, 4 raised to power 16. So that many coefficients are there. So even if you increase 1 qubit, the size of the density matrix increases to a very huge number. And that is what is a challenge with this density matrix formalism. So con of that is that, but it can simulate the most generic type of noises available. Another part what we are doing is we are trying to benchmark with the various application. So there are various algorithms that are available like QAOA, VQE, Mermin Bell. So these are some benchmarks that are available. We are trying to port the QSIM onto various accelerated platform, not only QSIM, but other simulators also we are benchmarking, and how much time it takes, what are the things if you introduce error, how much memory it consumes. So those kind of benchmarking thing we are looking at it. So there are few frameworks also available. Okay, so this output is from a framework called as a SupermarQ. It is an open source library that is commonly used for benchmarking your quantum computers also, simulators also. Okay, so you can look at it. It will give you some good benchmarks available. So this is output that we were able to get on QuASM simulator using quantum computing application oriented benchmark. So this is another benchmark framework that is available open source. You can make use of this benchmark for actually benchmarking application centric benchmark. Okay, I want to run Hamiltonian simulation onto a quantum computer. So how it will behave. So similarly, a Monte Carlo simulation, Grover search, quantum Fourier transform. So how your things behave according to the various application, you can benchmark these things. So we've been using these libraries for benchmarking simulators as well as the other advanced things. There is one more project that CDAC is also looking like development of quantum machine learning use cases. So these we are doing along with IIT like Roorkee, Ropar, Gandhinagar, Triple IIT Hyderabad. So CDAC 5 centers are involved. So we are trying to see how the quantum machine learning can help in the current areas where AI is being used. So whether we are getting any quantum advantage, whether we are getting any usability or not. So we are trying to port the application onto the quantum side and see the leverage that we are getting. So this quantum network simulator, I think it's a project that is done by CDAC Bangalore, I think. So here they simulate your quantum networks, how they do using some. So like QSIM, it has a different interface and people can use this particular thing. There is this project also. I think it's also from CDAC Bangalore, and other IITs are also involved in this. SETS is also involved. Just like IIT Madras is there, SETS is there, CDAC is there. So they are trying to do a metro area quantum access network and working on it. Recently, like CDAC is also looking into putting up a reference facility. So reference facility at CDAC Bangalore or Pune, it's to be decided, where your superconducting based quantum computers would be installed, maybe 50 to 100 qubit of quantum computers. So I think it's already a project in progress, and I think hopefully we'll get a reference facility within the next 2 years for superconducting in CDAC. So I think that was all from my side. So I think hopefully you have got an idea about what QSIM is and what CDAC is doing in the current areas. So I would be happy. So I think you can access the slides in this particular link, tinyurl.com QSIM 2024. So it will give you the link for the QSIM related things, the slides, the material I've been talking about, the links, and how to install it locally and all. So this is the link for the PPT, not this PPT, but the QSIM related PPT. So I think thank you very much. So I'm I think open for question. If you have any questions, you can cut it.
Participants, you are requested to unmute yourself and ask the questions.
Sir, can we run some machine learning type of applications in QSIM? If yes, then how?
Yeah, actually, see, QSIM is basically based on your Qiskit framework. Okay, so the Qiskit framework has a specific library available for machine learning, quantum machine learning. So the only thing is you need to install that particular package and you can use it. Like you install locally your QSIM, but only challenges that you would face is with the versions of frameworks that are available. So currently the QSIM works with a 0.20 version of the Qiskit framework. So corresponding version of your quantum machine learning library you need to install using pip. It's simple as that. So you can go through the tutorials of the Qiskit, how the machine learning works in Qiskit. The same program you can use as it is in the QSIM with minor modification that I have addressed in the like in the lecture.
So one more thing, I think QSIM, if we are implementing on laptop, it is only for Linux version of it.
See, it's a Python based thing. So
Yeah.
it does not make any difference whether you run it on Linux or whether you run it on the Windows. So in the Windows, if you have Python and you can install Anaconda or Miniconda, you can run QSIM.
Okay. Yes. So can you share your mail ID as well?
The mail ID is I think vivekn@cdac.in. I'll just maybe I'll write it in the comment section. vivekn@.in. So I have put my mail ID in the chat box.
Yes. It was a very informative session. So thanks.
Thank
Thank you.
you.
Any other question from participant side? Sir, there is one question in chat box. How quantum computing helpful in IoT applications? Can we use QC toolkit for IoT applications?
I would say IoT applications directly, like you cannot say it because ultimately what IoT application does is they aggregate the whole thing, send the data to main server, right? And in the main server, if you want to analyze things, okay, for analysis part, you can always use quantum. But direct as such, IoT and quantum, right now, it's not that much of a scope. But the machine learning kind of a thing is there. People are looking at what we can do with the machine learning and all, okay, in the quantum side. So similarly, the IoT, when you say you put data onto server and maybe the quantum can help you analyze that data, okay, like the classical AI counterpart does.
Any other question? Is there any question?
Okay, so I think if questions are not there, I think we can close the session. So thank
Yes.
you very much again for giving me an opportunity to talk about QSIM and bringing it to the people interested.
Just a minute, sir. Ma'am, screen is visible?
Yes, ma'am.
Yes. Yes, ma'am.
On behalf of everyone, I extend our deepest gratitude to Mr. Vivek Nanwal sir for his insightful and engaging presentation. His clear guidance has deepened our understanding of these complex topics and their importance in shaping a responsible and a secure future for this advanced technology. Sir, please accept our virtual token of appreciation.
Thank you very much.
Thank you, sir. We would also like to acknowledge and express our thanks to all the attendees. Your presence has made this session all the more meaningful and memorable. Thank you all. We will meet you again in tomorrow's session at 2 p.m. Thank you and have a good day.
Thank you very
Thank
much.
you, sir. Thanks for coming and giving such an informative session. Thanks a lot.
Sure, ma'am. Thank
Sir,
you.
is it possible that we will have a virtual tour at SIDAC, Hyderabad?
Uh, Actually, right now I'm not there.
Not right now, but
Yeah.
is it possible that we will have virtual tour?
Virtual tour, maybe we will talk it offline. Maybe if it is possible, I'll talk to my other seniors and all, and then maybe if it is possible, I'll let you know, ma'am.
Okay, sir. Okay. Thank you, sir.
Sure. Thank you very much.
Thank you.
Thank you, sir.
Thank you.
Participants are requested to fill feedback from attendance form, which is provided in the chat box. After filling the attendance, you can leave the session. Thank you. Thank you so much.